Refractive index of a medium is defined as the ratio of the speed of light in vacuum to the speed of light in that medium, and it's a positive quantity. And using Snell's law, we know that when light travels from rarer medium to denser medium, the refracted ray bends towards the normal, and when it travels from denser to rarer medium, the refracted ray bends away from the normal. Now, the question is, can the refractive index be a negative quantity? And if it can be a negative quantity, under what condition can it be negative? And when light enters a negative refractive index medium, how will the refracted ray bend? All these questions we are going to answer in this video. The refractive index of a medium can be expressed in terms of permittivity and permeability by using these formulas. So if I take the ratio, I can express M as like this. Now, in common dielectrics like mica or glass, the permittivity and permeability, they are positive quantities. So the refractive index is a positive quantity. But in certain class of materials known as metamaterials, which are artificially engineered materials, the permittivity and permeability can be negative. Suppose we have a metamaterial whose permittivity and permeability are negative. So mathematically, the product of these two quantities, it's a positive number. So we expect the refractive index to be positive. But it turns out it cannot be positive because we have to preserve the causality and the direction of energy flow. Basically, the physics has to be preserved. Now, to understand why, we should know that refractive index, it is more than just a number, a magnitude. It also carries the information of the wave propagation and energy flow. Here K, this is the wave vector, and it denotes the direction of the phase velocity, and S is the pointing vector. We also need to understand the difference between right-handed material and left-handed material. Let us take a 3D system, and the electric field is along the X direction, magnetic field is along the Y direction, and the phase velocity is along the Z direction. Now, from electromagnetic theory, we know the relation of the pointing vector in terms of E and B. It is given by the cross product of electric field and magnetic field divided by the permeability. And the average pointing vector, it will be along the phase velocity direction divided by mu. Now, if mu is positive, then E cross B will be along the Z direction. So S is parallel to the K direction, as is along the K direction. Now, if the permeability is negative, then E cross B is along the Z direction, but because of the negative permeability, S will be in the opposite direction. So from these two explanations, we can say that whenever the permeability is negative, the pointing vector, that is energy flow direction, is opposite to the phase velocity direction. We can classify the materials based on the four combination which we can obtain from permittivity and permeability. For example, if we have epsilon to be positive and mu to be positive, we call such type of material as double positive material. Next, when we have epsilon negative and mu positive, we have epsilon negative material. When epsilon is positive and mu is negative, we call it mu negative material. And when both of them are negative, we call as double negative material. Now, if the product of epsilon into mu is positive, then we can get a traveling wave. In the coming few seconds, I will be explaining why this condition is needed. So, this epsilon mu, the product of epsilon mu positive, can be obtained for DPS, that is double positive material, and such type of material are called right-handed material, and for double negative we call it left-handed material. Here the right-handed and left-handed is named based on whether the k vector is in parallel with the s vector or k vector is in opposite direction to the s vector. Now let us consider left-handed materials where epsilon and mu both are negative. Now, this two quantity being negative has a role to play. When mu is negative, we have already understood that the pointing vector will be antiparallel to the phase velocity direction. So the energy flow direction will be opposite to the direction of the phase velocity. Now for epsilon negative case, let us recall the formula of the magnitude of k. The magnitude of k is given by omega square root of the product of epsilon into mu. Now when both epsilon and mu are negative, the quantity inside the square root is a positive number. So the square root will give a real number. So k becomes a real number. So when k is a real number, we get a traveling wave. Now just try to imagine the scenario where epsilon is positive but mu is negative, or epsilon is negative and mu is positive. In that case, the product it's a negative number. So square root of a negative number, it gives an imaginary number. So whenever k is imaginary, the wave will be an evanescent wave. So the wave will decay with time and we will not be getting a traveling wave. So when epsilon is negative, in addition to mu negative, the product becomes positive, and this leads to the creation of or the condition of obtaining a traveling wave. Now let us recall the definition of refractive index. So refractive index depends on epsilon and mu. Now for left-handed material, there are two distinct features here. One is the pointing vector is antiparallel to the phase velocity. Another condition is for traveling wave to exist, the epsilon should be negative so that the product of epsilon and mu is positive. Now these two features, it is different from the right-handed materials. So in order to differentiate this exotic behavior, we take the refractive index to be negative for left-handed materials. This is how the negative refractive index comes into the picture. Now let us try to understand how the ray will bend when it enters a negative refractive index medium. So let us assume two medium. Medium 1, it has a positive refractive index, and medium 2, it has a negative refractive index. So we will incident a ray from medium 1 at an angle theta 1. Now let us use the Snell's law. So from Snell's law, we get this relation. Now here, N2 is negative. So since N2 is negative, sine theta 2 should be negative because the expression on the right hand side of the Snell's law, it's a positive quantity. So for that to happen, theta 2 should be negative. So the refracted ray will be on the same side with respect to the normal as the incident ray. So the refracted ray will look like this. Having a negative refractive index, it gives us a glimpse of the possibility of invisibility cloaks. But having negative refractive index, that is not the only criteria. We need many other conditions. For example, we have to artificially engineer the medium such that we have a space variation of permittivity and permeability. But the principle is, suppose we have an object and we have an artificially engineered medium around this object. So when the light ray comes, then it will be able to divert the ray around the object. Now, this invisibility clock, we are still in the early stages of research because the clock which is developed in laboratory work under certain conditions only. Like it, some reports are there where they have shown in microwave range or at specific angles. But still, negative refractive index is a step towards invisibility. Thank you everyone for watching.